English now because I received a request before. My name is Zacharias Yerasimou. I am a partner and technical director of Alpha Marine, and I'm very happy to welcome you to our presentation here. And I welcome you on board this interesting effort regarding the addressing the decarbonization technologies combined with the human factor developments. This is indeed a hot topic now in the market, and I'm very glad that jointly we will be able to discuss and see the challenges ahead. So before proceeding to the presentation, I will take advantage of this seminar to say a few things about our company, Alpha Marine. Just to say who we are and what we do, this is important. So Alpha Marine, as you know, have been in the industry for 38 years now, covering a wide range of technical HSQE management and training services. Very quickly, in technical aspects, we have been involved in all kinds of mechanical, electrical, and structural designs, all kinds of modifications, all kinds of conversions, all kinds of technical manuals, finite element analysis for structural designs, computer CFD analysis, and all kinds of conversions. Of course, we have been heavily involved in engineering studies, which is a hot topic in the market for ballast and scrubber retrofits. I need to say that in this specific area, we are commonly covering the whole range of the necessary services, starting from the 3D engineering, feasibility studies, detail engineering, and also attendance during installation. I need to mention here that we have also been very successful in the new building sector, and also we have also been involved in surveys, audits, and our services include also ship repairs, dry docks, preventing pre-post controls, navigational and cargo audits, as well as mooring audits. In the new building sector, as I said before, we typically cover the entire range of services, specification review, plan approval, and of course supervision, only on behalf of the owners. In the HSQE management systems, our office is normally developing, implementing, and optimizing management systems as per ISM and ISPS and ISM standards. Of course, TMSA, which is the hot topic, and this is the core business, one of the core business of our office. And of course, in line with RightShip requirements, dry BMS and CIRET 2.0, which is again an important topic in the market nowadays. Evidently, we extend our services in ISO standards like 50,000, 14,000, and 45,000. These services also, to mention that, include a new service, the Technical and Behavioral Competency Assessment and Verification, which is actually the integral part of the human factors. The latter will be, of course, be discussed and commented in the third part of this presentation. Evidently, all these services, I need to say that they are heavily supported by our internal certified training maritime center that actually prepares customized seminars and webinars, as well as CBDs towards enhancing the learning and the practical approach of the issue. Just to give you a quick overview of our activities in numbers, in the first slide, you can see new buildings plan approval and supervision, retrofit design and installations, surveys and audits, IHMs maintenance, TMSA audits, mooring management system plans, SEMS, MRVs, EXIs, and seminars. Of course, our services are not exhausted in this slide, but we thought that these are quite representative to meet this presentation. So, coming now to the decarbonization issue, which evidently it's the hottest topic in the market nowadays, and I assume that is why you are here with us. As you are very well aware, the shipping industry is under a transition period in all aspects, vertically and horizontally, in both technical and operation, as well as in HSQE. Technical and operation, the developments are coming through the need of decarbonization, through the reduction of CO2 emissions towards meeting the limits as set forth by IMO and recently by European Union, and also in the HSQE part through the introduction of new standards like dry BMS, CIRE 2.0, and risk. Have in mind that all these changes and developments, all these standards are following the recent introduction of ISGOT Edition 6. So someone can understand now that indeed, the maritime sector is under a huge transition period. Specifically now regarding the decarbonization transition, we strongly believe that the need for zero carbon ships and the necessary changes in the industry, and when I say industry, I mean the makers, I mean the infrastructure, I mean the ports and the supply chain itself, will certainly begin to affect the decisions of the operators and will have a real impact in both existing and new vessels in the market. Indeed, we have many things to learn, and the right decisions require collective knowledge of all market players. Being at the forefront of the maritime evolutionary progress, we aim as Alpha Marine to conceive the forthcoming changes in the field. We want to foresee the potential extents, and of course, we want to engineer with you solutions for their implementations on board the vessels. We had, of course, to ask ourselves two critical questions before getting involved in this. How we define ourselves in these changes, and what is our position and role in this progress? The answer for me and the team was more or less obvious, and I want to share with you. Our position in this chain of developments is to become the connecting link among the makers and institutions, together with classification societies, shipping companies, and of course the shipyards, towards assisting in three fundamental parameters. The first one, assisting in designing the process, contributing to the selection of the technologies with you, and of course, supporting the correct integration of the technologies on board the vessel. And as you know very well, based on your current experience with the ballast, this is the most important thing for a shipping company nowadays. These are the reasons why we in Alpha Marine Consulting, we choose to discuss this topic, and we choose that we want to be heavily involved in this constant transition and change in the maritime industry, together, of course, with you, being the main stakeholders in the market. This is exactly the reason we decided to gather together the changes affecting the two fundamental areas, the technical and the HSQE, and prepare this presentation in order to support you as our clients and global effort and contribute to the global efforts for a greener and an environmentally responsible market. Coming now to the presentations, just to say a few things. As I said before, in the first part of this presentation, we are actually gathering all the commonly used and well-known technologies, decarbonization technologies, while in the second part of the presentation, we are going to present the results of a case studies that we decided to apply on an Aframax tanker, dual fuel ready Aframax tanker, which was a new building of Atlas Maritime, and I want to thank Atlas very much and the owners. The case study actually is applying several decarbonization technologies on board the vessel, as well as a combination of such decarbonization technologies, aiming to check and calculate in real practice two main topics. First of all, we need to calculate the cost implications, which is obviously very important for the ship owners. And when I say cost implications, I mean the OPEX, the CAPEX, the fuel savings, obviously, and of course the payback period. Do not forget that this is an investment, a part of compliance with regulations. And secondly, we want to identify the expected CO2 reduction and, of course, the duration of the compliance period. This is, again, very important, and you will actually see this in the last slide of our conclusions. At the third part, we will, of course, as I said before, present and discussing the human factor developments in the shipping industry towards zero accidents and, of course, zero emissions. So, having said that, I need to thank you again for joining our seminar, and I will pass now the step to Mr. Georgios Kouris, who will present to you the first part of this presentation, gathering together, as I said, all the decarbonization technologies. Again, thank you very much.
Ladies and gentlemen, I would like to thank you also very much for attending this presentation. As already Mr. Yerasimou explained, today we are going to discuss regarding the importance of maritime industry, its contribution to greenhouse gas emission, and all available and emerging decarbonization technologies. A striking example of this is the feasibility study on an Aframax tanker, on which we implemented different decarbonization technologies with the main aim to assist ship owner to prepare for the upcoming regulations. The results and the case study itself will be further analyzed by Dr. Wu from University of Birmingham. Without doubt, shipping industry is the backbone of global economy. For the maritime industry, this is not just a moment of change, it's a time of transformation. Never have the decisions we face being so complex, and never have the consequences even matter more. We all have to be united under the common goal of carbon neutral tomorrow. However, to get there, decisions from vessel design to fuel choice need to be taken today, while cross-sector regulations and international collaborations will enable us to shape a brighter future. It's not about ensuring a future compliance or competitiveness. It's bigger than that. It's about shaping the future for the maritime industry, for our people, and for the world we are living in. As I said earlier, shipping is the backbone of global economy. According to United Nations Conference on Trade and Development, shipping is by far the most efficient mode of freight transport and transports almost 90% of the world trade volume. Greece ranks first globally in terms of capacity in ownership of commercial mechanized vessels. And while at the same time you can see on the right diagram that bulk carriers and oil tankers represent about 7 out of 10 vessels, let's say, globally. Also, LNG carriers and container vessels are also a very promising and booming sector. The last decade, shipping industry has been developed approximately by 67% and 3% compared to 2020. That means that as the shipping industry development increases, it generates increasing emissions. And this can be clearly seen on the right diagram again, where shipping industry emitted about 762 million tons of CO2 in 2020. Nowadays, shipping accounts approximately 2.2% of global greenhouse gas emissions, and these emissions are expected to increase further by 51% in 2050. It doesn't matter if we want an iPhone coming from China or a coffee from Mexico, or even to just tow an iceberg to Glasgow. At the end of the day, we all depend fundamentally in the shipping industry. And this just underscores the importance of decarbonizing the shipping sector. In 2018, International Maritime Organization adopted a greenhouse gas reduction strategy with a main goal to achieve zero emissions within this century, while at the same time requires 40% reduction of CO2 emissions per transport work by 2030 and 70% reduction of CO2 emissions by 2050. On the other hand, you can see with a light blue color line the European Union reduction strategy that requires net zero emissions by 2050. Now, let's find out which technology or fuel could drive shipping rates to zero. This is the question of this age, and for sure the question of the next decade. Deciding on the most appropriate solution depends on understanding the vessel's operation, safety of carriage, handling and storage, and availability at ports globally. While at the same time, we need to ensure that we can deliver to the shipping industry a safe, scalable, and commercially viable solution. There are several ways with which we can achieve high efficiency and compliance for our vessel. You can either switch to low carbon or zero carbon fuels. You can use technologies utilizing alternative energy sources like wind, sun. You can install a carbon capture storage technology, which is still under development. And of course, you can choose technologies that could potentially optimize the hull performance and the energy management of the vessel. So, firstly, we would like to give you an overview of the most alternative fuels. LNG and LPG are commonly used, are commonly known as transitional fuels nowadays, since the reduction in carbon dioxide emissions is limited. We can achieve up to 100% reduction in greenhouse gas emissions when ammonia, hydrogen, and methanol are used in the thermal fuel cells. Methanol is a liquid almost similar to the conventional marine fuels, which can be easily stored and handled on board. However, with potential, however, it needs more space in the market, and we need to accelerate this solution. Limited by the strong standards, hydrogen and ammonia are not commercially alternative fuels, but with high potential. Green production of hydrogen through electrolysis, powered by renewable energy, is possible. However, with increased cost at this stage due to the high price of electricity coming from renewables. Lastly, hydrogen, ammonia, and alcohols require larger tanks compared to conventional marine fuels. Secondly, let's focus on the first group of technologies utilizing alternative energy sources. Rotors, wind ventifoils, towing kinds are some of the technologies using the wind, having very high TRL level. However, the fuel consumption, the reduction in the fuel consumption and in the emissions depends on the vessel type, the size of the stand equipment, and the operations. Nuclear is nowadays the only solution that could lead shipping sector to carbon neutral future. However, radioactivity, waste disposal, and accidental release of radioactivity are the main reasons why the nuclear power has not been yet adopted in the maritime industry, especially in the commercial merchant vessels. Of course, there are alternative solutions instead of using uranium as a nuclear fuel, and this is a molten salt reactor, which has much less radioactive, which uses a fuel that is much less radioactive, and accidents such as nuclear meltdown are almost impossible. Cold ironing is another promising solution. However, the expensive infrastructure and the lack of standardization are some of the main disadvantages. For larger vessels like cruisers that require high hotel loadings, only limited ports can provide this facility. Then let's consider another group of technologies that aim to optimize the energy management of the vessel. Batteries can potentially reduce fuel consumption and emissions on board a vessel. However, the increased cost and the complexity of the system are the main disadvantages. Waste heat recovery is also another solution well proven nowadays on board vessels. However, the usage of this solution in the maritime industry depends on the different size, numbers of engines, and the efficiency, of course. Operating at a low speed, slow steaming, optimizing the route and the trim of the vessel are some of the operational measures that could lead to fuel savings and reduction on emission. However, this solution cannot lead the decarbonization, cannot lead the shipping industry in the decarbonization. Fuel cells, when powered by hydrogen, are fully renewable, can provide clean power. However, in this solution here, we have problems like availability of hydrogen fuel, and of course we need to increase further the manufacture of fuel cells. At the end of the day, we can also end up with hybrid and electric propulsion configuration in order to provide electrical power for our vessels. In this solution, we can combine combustion diesel engines, gas steam turbines, electrochemical power supply from fuel cells, for example, and wind assisted propulsion. Or even energy storage devices like flywheels and supercapacitors. So, last but not least, I would like to discuss regarding technologies that aim to capture the carbon dioxide on board the vessels. These technologies have low TRL level for maritime applications. It's a new concept for the maritime industry and can be considered as a short, medium-term solution that will meet the upcoming regulations and requirements until zero carbon emission fuels can be utilized for the shipping sector. And of course, carbon capture technology can the carbon dioxide emissions can be stored and as solid, liquid, or gas, depending on the technology used. Finally, let's deal with the technologies that aim to optimize the hull performance of the vessel. These technologies have a high TRL level, are already implemented in maritime industry, can have excellent return on investment for the ship owners, and of course we can achieve potential savings. Now, to sum up, I would like to go back again to the question, which solution do you think will drive shipping rates to zero? The simple fact is that at this stage, and as we stand now, there is no silver bullet or immediate answer. The solution lies to a range of technologies working together. And this is what Alpha Marine Consulting has proved during this study in collaboration with University of Birmingham, the results of which will be further analyzed by Dr. Wu. Thank you very much.
Thank you very much for the very nice introduction. I'm Dawei Wu. I'm from University of Birmingham. People may question why a university not near sea doing anything about marine stuff. Because previously I was working at Newcastle University as a senior lecturer of marine engineering. So it's very glad I can work with AMC on this project, because my expertise is hydrogen ammonia engine development. We do a lot of tests in the lab. So we really looking for what the science can be used in the engineering background, but also we decide it's time for us to do some practical thing. So that's we work with AMC, working on this case study about the Afra Max tank. So firstly, some information about this case study. Can you hear me? Sorry. So this is the ship specifications. You can see the length 250 meters and then the breadth 44 meters. That's you know very well. And the dead weight of the dead weight is 115,000 ton. And the engine you must be very familiar. And that's MAN engine. and the MCR is about 13,000 kilowatts, and there's also the 3 auxiliary engine, and the design speed of this vessel is 13 knots. And we have lots of inputs into this case study, especially the price. You can see the price for LSFO and the LNG over there. The price currently is very volatile. So we decided to apply a very large range to do the sensitivity analysis. So you can see the LSFO up to actually 1,200 US dollar per ton. And the LNG actually go up to 1,600 US dollar per ton. That's the price after war. And we understand the biofuel also very expensive, so we apply quite a large range on it. Hydrogen is an interesting one because we understand most hydrogen is still coming from fossil fuel using the steam reforming. The price we use 2.26. That is still based on the fossil fuel. The price of hydrogen we can get in the UK, which is 5 to 10 kilowatts. Pounds per kilogram. So which is still very, very expensive. That's from renewable energy, so still very expensive. So the carbon tax we apply here is 47. That's based on the April 2021 data from the EU. The last one, you can see the electricity. We get that electricity price for cold ironing purpose from one particular port in the EU. That's about 30 pence per kilowatt hour. About routes, we understand obviously the tanker can go anywhere, but we just want to make a very a particular case, which is from Rotterdam to Newark. So we look into the operational data. We understand the distance of this voyage, and we apply the ship speed of 13 knots on it. And the average travel day of each trip is about 25 days. So roughly, this ship traveling on sea is about 230 days a year. And the rest of the time, about 130 days, which is stay at port doing the cargo operating or just waiting. So very detailed information about this. Then we look into the configuration. So George already did a very comprehensive kind of review of what kind of technology we have we can apply onto the system. But if we really look into all those technologies, so the question is that is the system need to be so complicated? So if we look into this system, we can apply lots of different decarbonization technology into it. For example, obviously you can apply a dual fuel engine, you can apply the biofuel into your main engine. For the auxiliary engine side, the hotel load side, you can do the battery, you can apply fuel cell. You also can, having some load, that load could help you to reduce the fuel cost. For example, you can have the flattened rotor to install it. Then it will use some electricity from your auxiliary engine side, but it will help the propulsion side a lot. And also you can apply the air lubrication. Again, it will consume some electricity from your auxiliary engine, but it will reduce the friction, so help you reduce the fuel cost on your propulsion engine side. And you can see a very complicated system here. That is the carbon capture and storage. So that's a very hot topic. Lots of people talking at the moment. So we also look into that. But the whole system, is that necessary to be as complicated as that? Obviously, I think we need to break down this question to much easier cases. So we look into 9 different cases apart from the baseline. So the baseline is we just use that Alpha Max tank as the case based on a normal engine, use LSFO or MGO, whatever you like. We just make abbreviation as MGO So if we talk about MGO, you know that's the baseline case. Then also we have other cases. For example, the first one is use 10% biofuel blended into diesel. Secondly is using dual fuel. Obviously, that's a very popular modification of the engine. Then the third one is we not to replace one auxiliary engine. We apply battery, especially for the cargo operation, because we know the battery is very bulky, very large size. If you totally replace the auxiliary engine, obviously you don't have enough space to put it. So we just add battery into the whole system. And another case is very similar, use fuel cell to help the auxiliary engine in the hotel load side. Then the case 5, which is the rotors. This one is really, really interesting because it's draw a lot of market interest at the moment. Then we apply 2 cases. One is the traditional engine with rotors. The other one is the dual fuel engine with rotors. We can understand the decarbonization coming from where? Is that coming from the LNG engine side, or it's coming from the rotor? Then the last 3 cases, case 7 and case 8, we're talking about some technology, in the future. The first one is we use CCS, carbon capture and storage, with a diesel engine. Then the case 8 is CCS going with a dual fuel engine. So we could understand how much carbon we can capture on the vessel. The last one is a dual fuel engine with the air lubrication. That's also available on the market. Okay, let's have a look of the detailed cases. I'm trying not to overwhelm you about those detailed information, but we can look into this base case. The thing we can understand is that about 80%. I have to say one thing beforehand. This is the CapEx, but the CapEx is only about the powertrain system. So it's not including the shipbuilding, everything. It's just about the powertrain. Everything generates the power for propulsion or the power for auxiliary purpose. Then we include it in this CapEx, not everything. Okay, the marine engine and auxiliary engine in total takes about 80% of the cost of the CapEx of this tank. And the fuel storage tank takes about 14%. If you have those numbers in your mind, then we move on to look into how the other cases compare with the baseline one. Okay, this one is the biofuel. Actually, biofuel not change this CapEx table too much. It's just increased a little bit on the your main engine because you just need to do some modification of your inject timing, inject duration, and a little bit cost. Maybe you need slightly bigger storage tank because the biofuel having less heating value within it compared to your LSFO. Then move on to the next one is the dual fuel case. In the dual fuel case, interestingly, you can see that the fuel storage tank that cost overtake the auxiliary engine becomes the second place. So you need to do some investment into that. And looking at the GA, then AMC already designed this kind of LNG ready ship. So you can see where to put the LNG storage tank on board. Okay. The next one, we're looking at the battery involved into this powertrain. We cannot install a too big battery. We only trying to use the battery to help the cargo operation. So this battery is about 16,960 kilowatt hour. I'll give you a more kind of familiar idea. So on a peak time, it can generate about 1,800 kilowatts power to help. But that power won't last long because the energy stored in this battery is limited. So you can last about 9 hours for that peak power. Obviously, the cargo operation, you're probably talking about more than 2,000 kilowatts at port. So you won't only use battery to serve for that purpose. you obviously have the engine working for the base, this kind of power demand. Then the battery is helping your auxiliary engine for the cargo operation. But even in that case, the battery takes a lot of space. The battery takes about 6 container size to deliver that job. And also its weight is 106 ton for that. Looking into the CapEx table, the battery cost takes about almost 20% of the powertrain, apart from the marine engine and the auxiliary engine. So let's look into the other case about the fuel cell. So the fuel cell, we apply something very similar to an engine. It's about 800 kilowatt output. So basically, it's working as the auxiliary engine. The difference between the fuel cell technology and the auxiliary engine is the fuel cell cannot respond to your demand very quickly. So if you want to increase the power output from the fuel cell, you're talking about a couple minutes delay at least. So, but in terms of the size, the volume of the fuel cell, it's much smaller compared to the battery bank. So if you need to have this 800 kilowatts fuel cell on board, you only need 1 container size. This you can put here to support your whole system. And there's a downside of using fuel cell, which is the hydrogen storage. Hydrogen storage tank is currently talking very, very expensive. We have some cost in the later slides. So even you only supply this one fuel cell about 800 kilowatts, you're still talking about the major investments into your fuel storage tank. Then you can see your fuel storage tank cost, capex, increase to almost 30%. Close to. Okay, the next one is use the rotor to going along with the powertrain system. So this case, we install 2 flattened rotor into the onto the deck. Obviously, this is the diesel engine, so potentially we don't have the LNG tank on the deck. So we can even install 3 on the vessel, which can contribute more to the decarbonization. But we want to compare the diesel case with the LNG case. So we still install 2. Remember that for LNG case, we have the storage tank on board. Looking at this case, then you will find that you can install 2 35-meter tall and a 5-meter diameter rotor onto your deck. Then looking into the cost, it's not cheap, so it takes quite a lot, 30%. But this is the relative value. It's just break down to the percentage. But if you will, in the next slide, to see the absolute value of that, it's still a decent investment after our research. Then this is 2 rotor case without LNG tank. The next one is the LNG tank with the 2 rotors. Very similar setup. The only thing is this is the LNG engine. So the cost and the LNG storage tank will take some share from this capex pie. These 2 coming case is about the CCS. We know CCS for marine application is still not on market yet. So what we do is that we find some CCS case products which is designed for the power plants. Then we scale down to the right size for the this tanker, then apply onto it. So when looking at this kind of design, the CCS part actually will dominate your powertrain capex. It takes about 40%, even higher, of your investment. So the investment is really, really major. And it will also increase the complexity of your system. So it requires electricity input because you need to have the compressor. Also, you need use the waste heat from your engine as well. So that's talking about quite a lot kind of modification of your system. So you can see this red orange box represents your CO2 storage tank. There's different way to store CO2, but obviously if you liquefy it, you can take the minimum volume space on your ship. So it will be a preferred way. Looking to the design, if you have the diesel engine, this kind of baseline ship, you don't have the cryogenic energy. You don't know where it's coming from. So you have to set up another refrigeration system to liquefy the CO2 on board, then stored in your CO2 storage tank to minimize its volume. But if you go to the next case, which is the it's back. So this is the dual fuel case. So if you go to a dual fuel case, you would be able to use the cryogenic energy from the liquefied natural gas. Because when you use the liquefied natural gas, you need to evaporate it. So lots of cryogenic energy will be released. Okay. Finally, come to the last case, which is the air lubrication. So the air lubrication, again, we talking about quite a lot investment, but not as big as the rotor. It only takes about 12% of the whole system. And when you talk with the supplier, you potentially find some discount on it. So you can even decrease that to 10% in the late stage of our study. Okay, I hope not overwhelm you with all this kind of boring technologies. Let's go for the cost. Okay, so that's, I think, what you're really interested about. Okay, so let's look into the CapEx comparison of all those powertrain designs. We try to hiding the supply information, so we normalize the cost. So the MGO you can see is the baseline case. We just make it as unit, as one. So the rest of the cases you can see, all of them will have a higher cost compared to the baseline. That's quite easy to understand. The BD10, which is the biofuel case, you just need to slightly increase your cost. But we would understand that later. Your fuel cost will dramatically increase due to the biofuel supply and the cost. Then the other information you can get from this diagram is like the battery and the fuel cell. You're talking about very high cost to adding this system onto your powertrain. Although it won't take too much, share of your auxiliary power. So there's, you can see lots of things. In terms of the rotor, the investment is moderate, but we will find later if it brings any benefit for your fuel cost and other costs as well. For the CCS, especially for the MGO baseline case plus CCS this case, it needs extra refrigeration system. So the investment is quite huge. Although in the later you will see the carbon reduction is also quite large as well. Lastly, the air lubrication, the cost on top of your current powertrain, not big, but it can bring kind of moderate, less than 10%, this kind of fuel saving. Okay, let's keep looking the next one. So this is the total cost. When you're adding the fuel cost on top of the CapEx, everything, you will see the cost over 25 years just soar up to a very high level. Then looking these two rotor case, you will understand that the rotor really helps you a lot in terms of the cost saving over 25 years. And these red bits, they are reflex. So when you're using battery, using CCS, you're talking about not only the initial investment, you're also talking about some replace cost during the lifespan of your vessel. So this also needs to be considered. On the right-hand side, this diagram shows you, well, currently there's no carbon tax applied yet. So when you thinking about the carbon tax on top of the current total cost over 25 years, then you will see those red-orange bits on the top of it. The size of this column of carbon tax, it depends on how much carbon dioxide emission coming from your system. Okay. So again, the two rotor case, it do give you kind of a very good good total cost over 25 years. I think operator also interesting about the fuel total fuel cost. So when looking into these three diagrams, on the left-hand side, you can see that the fuel cost depends on how many metric ton you used for this vessel. Again, it is over, I think over, that's a single trip. That's not over 25 years. That's a return trip from Rotterdam to New York and a return. Okay, so this one give you some information, but not really, because the density of those fuels and the heating value of those fuels not exactly the same. For example, you can see the hydrogen. It's very light, only very small bit you can find here. But we need to look into the other side of this kind of information. So we do the equivalent MGO consumption. So we convert all the fuel consumption into MGO. Then we can understand very well which case save a lot of fuel cost. So so on this side, we find two rotors really save a lot of cost, and the air lubrication also help us to save. But the rest of the cases, like the biofuel, actually you would looking at increase a bit. On the right-hand side, you have this fuel volume for one round trip information. That's also a crucial information. The hydrogen I'm talking about, it takes a lot of space. So when you're looking at the volume of your fuel tank, that will increase a lot. Okay, then it is the payback period and the levelized cost of electricity. There's two kind of criteria help you to judge which one give you the best economic viability. So on the left-hand side, the baseline, you're talking about 8 years for the payback of this powertrain system, not the whole ship. But when you're looking at the other systems, when you're adding some technology on it, you will just prolong the payback period a little, not too much. But when you're using the battery technology or the biofuel, you're potentially looking at very long payback periods. Okay, so that's the cost information. Then another part of information you will be very interesting is the carbon emissions. How much carbon you would save. So looking at this diagram, so this is the baseline. That's over 25 years, how much CO2 emitted. And we use $47 per ton as the unit price to calculate how much carbon penalty you're talking about over 25 years. And different cases would save CO2 emission. The best case we're looking at is the dual fuel engine plus CCS. It saves almost 35% of the carbon emission from the system. But obviously this one, you would know that it's cost a lot. This side, the carbon price actually is undecided yet. So we do the sensitivity analysis to look into the carbon tax from $20 per ton to $90 per ton. So you can see it's increased linearly. So if you don't do any kind of action now, you're talking about a much more kind of carbon penalty when the carbon tax increased to $90 per ton. Right, this one is about the GWP 20 and GWP 100. So these two information talking about not only CO2 emission, it's also included other global warming effect gases like the methane. So you can see that DF case, the GWP 20 actually is increased rather than reduced. But over the long run, for GWP 100, you're talking about the major reduction of the CO2. On the right-hand side, we calculate all the EEDI of all those cases. So we can see for the IMO targets until 2025, basically all the cases, they're fine. But the biofuel case is only the exceptional. They are not meets the 2025 results. Okay, this diagram shows the return of investment for those technologies you add onto your powertrain system. So the rotor talking about 4 to 5 years payback period only for that device, and for the air lubrication, you talking about 6 to 8 years. But it again depends on how much CO2 penalty you could save using those technologies. You can see the air lubrication, you have to have very high CO2, have to have very high this kind of CO2 tax. Then you're talking about it's reduced the payback period to about 6 years. Otherwise, no carbon tax, that will be 8 years. For the CCS, it can very quickly to reduce the carbon emission. But the problem is that the cost of it, if you not reach $50 per ton, you won't have any kind of payback period within 25 years. Okay, so I think I probably skip a couple slides to reach the our conclusion. So so the message we want to pass over to you is that if looking at the CO2 emission based on different cases, we're looking at most of the cases we propose here will be in compliance with the IMO that's reduction strategy until 2025. But if you're not taking any action for the MGO baseline case, after that, you have to do some modification on your current vessels. The other case, like biofuel, dual fuel, or adding like battery fuel cell or rotors, they can reach 2030. So it's kind of a moderate modification can allow you to extend the compliance until that time. Then the CCS, obviously, you can see a very good compliance with the IMO strategy, but the problem is that their cost is really, really high. Let's just conclude the conclusion of our slides. So firstly is the baseline case will not in compliance with this IMO strategy as early as 2025. So the dual fuel case achieve carbon reduction, which follows the IMO strategy towards 2030, even without any add-on technologies. After 2030, you obviously can add more technology onto it, make sure that it will be a major carbon reduction. And we find that rotors are very good option with quite short payback periods and achieve very good CO2 reduction effect. And the battery and the fuel cell, it looks not the immediate solution. It's too expensive, and their carbon reduction is moderate. It's not major at all. If the IMO 2050 targets are to be met, So several CO2 reduction technologies have to be used in tandem, which means that you need to apply the modification of this part firstly, then keep doing the modification in the moderate modification, then finally follow this IMO reduction strategy. So that's the major finding we found from our study. Sorry, I just have a very quick last couple slides. So based on this case study, we developed a decision-making tool to let you understand if your vessel applies certain modification can be in compliance with the IMO strategy. So we have a very well-organized structure already. So initially, we can put in some performance information into our simulation. Then the simulation output will put into the Power BI, which is a data source, data treatment, this kind of software. Again, with the ship operation data, we can generate some visualization to let you understand some information very quickly. For example, the next slides, you can understand the ship system, what's its performance, how much CO2 emission, and how much fuel it will consume very, very quickly. And also you can try to predict the cost effectiveness of your new technology. What's the CapEx breakdown? What's the payback period? And also what's the fuel cost over 25 years? Okay, I think that's everything from me. Sorry, overrun for 3 minutes. Yeah, thank you.
Hello, I'm Nikos Andreadis. I'm managing the development of human factor protocols in Alpha Marine. I would like to thank my colleagues and the professor for the very interesting presentations they have made. It's always very interesting to see the challenges that our technical department has always to overcome in order to help companies adapt new technologies and simulate new stuff and make shipping not only greener but safer as well. Nevertheless, we will see that although automation and new technologies have been adapted by shipping industry over the past decades successfully, keep in mind double hull all the actis, shipping became safer but not safe enough. And this is because we have a very complicated variable introduced into this system. And this variable actually is the human factor. Can you help me change the slide, please? It seems that we have a small technical problem, but we will solve it out. Anyways, just in the system that we have and we want to make safer, for example, the operation of a vessel, we have something that introduces great variability. This variability can be either positive or negative. Let me see if I can change that. That's absolutely fantastic. Thank you. Now, how this variability will be introduced and how it will be developed is in great extent in our hands. The human factor as a concept I've seen from our visit and collaboration with various companies is that we misjudge it. We narrowed it down to the individual characteristics like the physical, psychological, social, or competency of persons. However, it's much more complicated than that. It's the context as well. Imagine that if you have imagine that you have a seafarer who is quite competent, they know what they do, however, they need to work under severe pressure, have conflicting priorities, okay? You have to navigate the vessel during this strict deadline, but safety first, of course. They haven't slept very well. They are very demotivated because they have been blamed for something that they haven't done. And they have to do a lot of things. What are the chances that the seafarer will actually, and the team will perform and fail? The chances are quite high. So the most important variable when we are discussing about human factors is the context that people operate. This is what makes the difference. This is what can make variability either a positive one, and people can mitigate risks, or can make people make mistakes. And after decades of studies and unfortunately incidents, and we will see some, we have concluded, and we know that this is context that influences performance, and usually, as a rule, people can make safety work. So people can perform. However, usually there are contextual variables that are obstacles to them. How we know that? Through the hard way. I am quite sure that at least some of you or all of you at least know one of these major failures. The NASA, the Challenger one, maybe the older of the audience know, you have seen it on TV, Costa Concordia, Boeing, the 737 MAX failures, BP, Exxon Valdez, and the BP, the Deep Water Horizon. All these failures actually were attributed to contextual variables. Initially, especially for the Boeing case, the attribution of the failure was towards the people. Of course, that was scapegoating and blame culture. And when we looked deeper for all these companies, we've seen that the truth lied beneath the surface. It was not simple as that somebody was incompetent and they failed. It was far more complex. And what we have found, guess what? See how many keywords here. The NASA disaster actually had to do a lot with culture. There was a lot of politicization, multiple projects that they had to run, tight deadlines. They felt safe that they know what they were doing. They had what we call a group thinking mentality. So everybody was deciding towards the direction that they desired, they wanted to deliver. Nobody actually was eager to be the unpleasant guy. This is group thinking, and you will see it. We have exactly the same problem in other failures as well, in BP as well. Costa Concordia, people on board were not having teamwork, situation awareness, many problems that relate directly to behavioral competencies. Exxon Valdez, insufficient crewing, bad maintenance of critical components, so the CAS radar was not functioning. This was Exxon to blame, and many, many, many other things. Now, all these things that you see here, they were lurking behind for a substantial amount of time. They were not present there just for some hours or a day. They were there for months. Now, the question that we usually pose to shipping companies is, how are you sure that under your surface, under your iceberg, these things are not lurking behind? The answer is that we are not. Okay, and that's why the industry actually tries to make us look deep inside and find out, because these variables lurk behind our companies as well. The big question here is, are we similar to these companies? Do we share similarities? The answer is yes. As with the companies that we have just, I have just described to you, we operate in highly competitive commercial environments. So we have a lot of commercial pressures, conflicting priorities, hierarchical management systems, skilled employees that they have their own career paths and their own priorities within our cultures. We are strictly regulated, and we have similar technologies and obstacles to pass. So we are very, very, very similar. And how this translates to the results in our industry, you will see that even in our industry, and even after so many technologies and automations and many, many other things that have been introduced after decades of development, we still have human error being responsible for 75%, maybe more, of the incident and the accidents that we have. And if you see the keywords here, you will see that the keywords, this deadly dozen that we have in the industry, is very, very similar to what we've seen about Boeing, what we've seen about NASA, and so on and so forth. So you see, we have exactly the same problems, and we are exactly the same risks that these very, very big companies, these very big institutions have. what we need to do, up until now, we have focused extensively on this pyramid, on the two top parts. So we are quite good with technologies, we have processes, we have systems, and we are actually quite good on that. Nevertheless, what we are not quite good is the basis of the pyramid. And this is where the problem, and this is where the major improvements can come. Now, you see that this is the most difficult part to tackle. However, if we manage to do it, and I believe that we do with the tools that we have, we will have long-term effects, and we will minimize error, minimize failure, and minimize accidents. The industry helps us a lot, and we have already a lot of frameworks and guidance that drives us towards this direction. We have Intertanko, we have OKIMF, Dry BMS, RightShip, that they have published all these very good tools, very beautiful tools that we need to understand and assimilate. But before we go to how to, we need to understand the basic principles that underlie these frameworks, the mentality that lies beneath. And of course, the mentality that lies beneath has to do with the incidents that we've seen. We have learned the hard way. So we have some specific facts that we have derived over the years. So fact number one, human errors are universal and inevitable. So errors will happen any day, anytime, aboard the vessel, on the office. It will always be there. Now, the whole idea is, okay, how we can mitigate the risk, how we can increase the positive behaviors of people, the skills of people, so when errors come, they can actually absorb it and develop an error management culture. Now, fact number two, people cannot easily avoid those actions. Okay, they don't do errors because they like it. They don't do errors because they want it. They do errors because it makes sense to them. Okay, errors is something that we understand in retrospect. That somebody make an error. Error is defined by the result, let's say. Errors are consequences rather than causes. That means that error actually is derived by the environment, by the context that the person made the error. Okay, if, for example, I have somebody who needs to operate in a very dark light with a very humid, high temperatures, this is not a very good environment to make very complicated decisions. Okay, so the consequences of the error might not be the skill of the person, but rather the environment that the person had to operate. Many errors fall into recurrent patterns, so we can see that people, if you study them, you will see that if you put them under the same conditions, statistically speaking, they will make the same errors. So we know, in a sense, we can predict behavior. So that gives us a tool. If I can predict behavior, if I know what people can do, I can take measures. That's good for us, right? So lessons learned from the industry and the various industries. Now, same or similar events have often occurred before, and we need to learn from these errors, and we do. Now, the last 5 facts, very important facts. The best people can make the worst mistakes. If you study the 737 MAX cases or the NASA case or the BP case, you will see that the people involved on the problem and the people that they made the wrong decisions and the error were extremely highly skilled people. Extremely. MIT, Harvard, very good professionals, very, very, very experienced. And I think we can agree that they didn't want all these things to happen. However, it happened. So we cannot rely on experience. And this is what we do in the industry sometimes. We rely on experience. We say, okay, I have a master. He's very good. He has sailed so many times. He's okay. I rely on him. This is a false safety perception that we have, and this is absolutely wrong. Because this specific person, the very experienced master, if I put him in the wrong context and the wrong condition, he will probably fail. Now, similar type of errors occur on all industries. Again, the type of errors, and you'll see that we can categorize it and understand it, occur in all industries. That gives us the benefit that we can learn and understand. And because shipping, actually, we are falling behind in relation to aviation or nuclear power plants and so on and so forth, we are in a sense lucky that we can get the lessons learned from their disasters mostly. So we need to assimilate and adapt it. Safety significant failures can occur at all levels of the system. That means the top management can make errors, and these errors can be transfused and transposed to the rest of the system. And if you study deeply the cases that we are discussing, you will see that the top management decisions and the culture was heavily involved and implicated on these major disasters. There are certain situations and conditions that lead people into the same error. I think we have covered that, and I hope it's clear by now. The last one, and I think the most important, we cannot change human condition, we cannot change the human brain, but we can change the condition which humans work. This is where we can interfere, and this is where we can make things better. And I know that it sounds complicated, but trust me, it's not. It works, and we can do it. We have designed and we know how to show you and show the industry how to achieve this target. Now, if we take all these 10 facts and try to have these simple rules, and these simple rules, keep them as a tool in your mind, because if you have these simple rules and you manage a department or you manage a company, immediately you look towards the right direction on improving your human factors and the people and the conditions that they work. So, number one, if we take all these facts and we make some 5 principles, you will see that we need to understand that error is normal. It's a part of the system. Okay, people are dynamic creatures. The systems that we need to operate are dynamic. There is no way, absolutely no way, that we can control it 100%. So, if we cannot control it, we need to manage it. We need to have barriers. We need to increase the skills in order to create buffers and obstacles from errors to develop into crisis. So error is normal. Everybody will make a mistake. We need to go away from blaming people. Okay? This is one of the biggest mistakes that we do when we have these very small errors or small failures within our companies is that we blame people. It's your fault. Get out of here. You will lose your job or something like that. This is absolutely wrong because it creates a very, very, very wrong culture where people are not open to contribute, to speak, to help us improve. Learning and improving is vital. So instead of blaming people, we need to understand why they made an error, why they have failed. If we understand why they have failed, we are targeting the root cause. Even let me tell you an alternative. If I fire somebody who failed and I bring another one, the person that I brought in the new position, if I put the person in the same condition, the same context, statistically the person will fail again. So it's not the person that I need to, decapitate and send away. I need to change the context, the root cause of the problem. Now, context influences behavior. So this is how we need to start understanding things. We need not who did it, but why it happened. This is the correct question. Why a failure happened? What was not there or what was there? How you respond to failure matters. This is the leadership position. If you respond with blaming, you have a bad culture. People will try to hide things from you. They will not participate in the learning process. They will be demotivated. They will not be accountable. And you actually, by responding with a blaming culture, you increase the context that is negative around people. Now, let's move on to how we can make things work, how we can actually understand the whole context and the system and everything. First of all, we need to have a methodical approach. In Alpha Marine, we believe in a step-by-step design and consolidation of certain phases. So phase 1, of course, we have systems, we have processes. We need to evolve and update the backbone of our companies, our SMSs. So the first things that we need to do is see where our systems needs to be improved. Okay? We have some gaps. We need to introduce new tools. We need to update some obsolete ones. And we need to make our systems simpler. we need to minimize them. We need to make them more friendly to the user without exclude all unnecessary informations. In the heart of this phase one, we need to develop solid competence management systems. So this is how we create buffers. We increase the competence of people on their capacity to tackle error. Now, number two, we need to understand that we need to identify these core performance shaping factors, or if you want, human factor KPIs. The deadly dozen that we've seen in the beginning gives us a solid basis for this. However, there are more than that, but the deadly dozen is a very, very good start. So if we know what to measure and how to measure it, now step by step, we are becoming in control of the system. Now, if I know what's going on, and if I can quantify what's going on and what is important, the next step is to intervene. So now I have targeted actions. Usually until now, we have these horizontal actions. We have a problem and we make these horizontal campaigns. We make trainings to everybody. Okay, these are not targeted actions. These are horizontal. They target everything. And trust me, they don't work. Or we resort sometimes to isolated actions. We do some isolated safety culture surveys, and that's it. Although these may be important and they might bring some value, they are not the solution to the problem. They are temporary fixes, band-aids. They don't fix, they don't cure the Now, the last one is that as long as we understand what are the important human factor KPIs, how we will measure it, and how we can intervene, we can use these KPIs as leading indicators. Because all these things that we have discussed and the deadly dozen are variables that precede an event. For example, if I have high levels of stress on board, or I have high levels of fatigue on board, I know statistically that my risk is elevated. And this will probably, I'm at risk of having something quite serious, all right? Now, how we approach this complicated, let's say, problem. Now, we have three pillars of actions. The first pillar of action has to do with culture. So we need to target with specific actions that we know that we want the culture part. The second one is that we need to focus on competency and improve competency. The third one is that we need to develop the learning capability of our systems, of our companies. You will see that there are a lot of actions, and there are a lot of tools that we can use. Some of them are basic, some of them we already have them in our systems, some may need update, and some are quite advanced. However, this collection of tools, if you incorporate it into your systems and you implement it correctly, they make a difference. Of course, if we can take the fundamental, the basic, the core idea of each one of the pillars, the blame culture is the one that first and foremost we need to tackle in our companies. Blaming is quite bad, characterized shipping up to now. Many shipping companies are making efforts to get past that and change the mindset of crew members and seafarers. You see, if we manage to consolidate a no-blaming culture in our companies, we will have people that they are all around the place in the front line, that they will try to contribute, find facts, contribute in lessons learned, give us best practices, admit they made a mistake, don't try to hide, be accountable, and so on and so forth. I have a lot of pressure from our technical director, as always. So, a good competency management system is core. The competency management systems that we now have in shipping are static. So we have some forms, and we having interviews and soft skills, technical skills. We appraise on certain factors and so on and so forth. This is not bad, but this is not exactly what we need to do. The system needs to be dynamic. So we need to feed into the competence system our lessons learned. We need to feed into the system things, PSFs, human factor KPIs that we know that need improvement, that they are vital for our companies. We need to fit them back and select people that they match their performance. Appraise people based on this kind of KPIs. This is the way it works. On the heart of this system lies the behavioral competency stuff. Now, we are lucky enough because in shipping now, we have two major frameworks. One came from InterTango, and this is applicable to bulkers as well. So we have the technical competencies, very specific criteria for navigation, mooring, in order to appraise people, in order to choose people, in order to train people. We have frameworks of objective and systematic criteria. The same one with behavioral competencies. So we target soft skills. And we have a framework with specific indicators that we can get trained, we can implement, we can target. All these things that you see here can also be used as human factor KPIs, as performance shaping factors. Okay, I can measure teamwork in my system. Of course, very, very important, we need to understand and specialize on human failure and categorize human failure accordingly. So we need to understand what are the differences between error and non-compliance. We need to understand what are action errors, what are thinking errors. And this is not very difficult to understand. If you see one example from each one of the categories, you will understand it. When you understand what is going on, then you can actually map it. You can, if you do a walkthrough on board the vessel and you see somebody performing something and you see an error, you will understand why the person did the error. Okay? Did they make the mistake? Did they omit something? Did they make the shortcut? All are different. If you understand the actions, the performance safety factors will be adapted accordingly. So I know, for example, that I need to develop a checklist because people make action errors. Okay, they omit things because they need to remember, for example. Okay? Now, on the learning part, if I have all these human factor KPIs in a coherent manner, and I measure them correctly and target it, all these KPIs, and I told you that the Deadly Dozen is a very good starting point, I will develop a leading indicators. Leading indicators will help me predict. So whenever I see these human factor KPIs, these performance shaping factors rise in a bad way, then this will alarm me, and that will mean that I need to take action before I have a problem, before I have a lagging indicator going up. LTIF, for example, is one of these things. The whole bet is that by using all this stuff to move from the reactive position, from the reactive level that we are currently at, and move towards the level 2, 3, and hopefully 4 levels, with a proactive culture. So we need to ensure that we tackle and fix things before they happen. And this is the way to do it. Now, to close the seminar today, we have seen that how important the new technologies are and how they have made shipping greener and safer, and they will continue to do so. However, it's not the vessel, it's human performance. People, until vessels become fully automatic, people will be a part of the system. So as long as humans are part of the system, the variability that they introduce, they will cause problems. Okay, so humans remain the main drivers of performance, even in the age of increased automation. So number 2, technology is part of the answer, but it's not part of the solution. So we can have automation, we can have the best vessels, we can have perfect radars, we can have everything. However, if human competency, the humans on board are not capable, or they cannot function because the system, the context is very bad, errors and failures will occur. So we need to understand how we need to combine. Keep in mind that from the introduction of electronic radars, EGDIS, and so on and so forth on board, this had an effect on the new age, let's say, seafarers, and they don't have external situation awareness as they used to have as the old generations. So automation and systems are not always the cure. They have some drawbacks as well that we need to understand and tackle. So people need to be trained to have external situational aware as well, and not simply rely on a system that may fail as well. So we need to shift from emphasis on technology and not rely solely on technology, and focus on the human factors and how humans interact with all the systems, and how we can increase their capability to act as buffers, as a system within a system that mitigates risk. Okay, because this is what seafarers do. 90% of the vessel today will reach their destination in a safe manner. That doesn't mean that everything went well on board. However, there were humans on board that they managed to tackle errors, they managed to mitigate risks, to solve problems. This is what they did, and we need to increase their capacity to do so even more. That's all from me. Keep in mind these two rules, and we are done for today.
Thank you very much. If you do have questions, or if you have a question later on, please email us and we will ensure that to reply back to you. Yes.
Yes, thank you very much. Excellent presentations. A question on the total cost for the decarbonization that the professor has done. You have looked at the total cost, CapEx, when you're looking at it and how much you can reduce the carbon. But did you include the OpEx as well? Because different system will require an additional cost in operation, whether it's a chemical you have to do, or training people, or adding manpower. So is that something you considered?
Yes, we consider that. So when it affects the total cost, not only the carbon tax bit, but also because of the reduction, you also cost the reduction of the fuel cost, other costs. We also apply the factor onto it. So you would get the results, reflect not only the capex bit or the carbon penalty bit, but also the OPEX will be affected as well.
Okay, thank you. And one more, I'm sorry I'm taking the time. Why use B10 and you didn't use B30, for example? I mean, a different composition of biofuel, higher composition of biofuel.
Because this biofuel actually we get from one company and test it in our engine.
Yes.
So we're very familiar with this biofuel. So that's why we use that as example. But other biofuel, it's very difficult to get exactly the market price, because they are most of them in the laboratory stage. They cannot tell us exactly the market price, which is not good to be used in the cost analysis.
Thank you.
Just to say that we have to select either B10 or B20 or B30. But at the time that we had to compile the presentation, we had input for B10, so we choose that one. However, I believe that it will not substantially change the results of the comparison between the technologies. So let's keep not the absolute numbers, because if you saw in the presentation, we have not included absolute numbers. We want to show the comparison between the technologies. It doesn't make any sense at this time to present any absolute values. We only need to present the relative cost between the technologies. That was the reason we chose B10. Any other question? Okay, so since we're a little bit late, I want to thank you very much on behalf of all the members and employees of Alpha Marine Consulting. I want to personally thank Professor Wu for his effort, Mr. Georgios Kouris, Nikos Andreadis, and of course Pavlos Diamantis and Kostas Adrianos for their efforts to prepare this, I hope, interesting presentation, combining and showing to you the challenges of the decarbonization combined with the human factor developments in the market. Again, I need to thank you very much. And at this right step, as we discuss now, I want to announce, Mr. Wu already announced, the introduction of our decarbonization tool of the market, and we hope that we will be able to develop further and soon you will be learning news from us. Thank you very much again for your presence, and hope to see you soon. Thank you very much.